This program is being presented to you by the Heraeus International Winter School on Gravity and Light.
Good morning and welcome to the 9th lecture of the Winter School. Today's lecture number 9 is titled Newtonian Spacetime is Curved. This may come as a shock because you thought probably it isn't curved, and indeed in the standard formulation it is not. The question is whether this standard formulation holds up. Of course it does, in a way. But if we inspect the axioms properly, I would like to make the point that Newtonian spacetime must be considered curved, and in fact that this curvature absorbs the effect of a gravitational force, so that no longer gravity can be considered a force. Let me make my point. Let's start in the beginning. Oh, and you see, today is a physics lecture. However, we'll of course use much of what we have learned, especially the autoparallel equation. And we start here by Newton's two laws, which I wrote down more or less like Newton did. Newton didn't use formulae. He made little drawings and he used words, but it's actually very carefully worded. So the first axiom is a body on which no force acts moves uniformly along a straight line. And usually there is the addition in an inertial system. And Newton too also has the addition in an inertial system. I did not put that there because an inertial system has something to do with choosing coordinates. But this statement is an absolute statement. A body on which no force acts moves uniformly along a straight line. We know what a straight line is independent of our reference system, right? Or we can at least formulate this today. Second, deviation of a body's motion from such uniform straight motion, so deviation, today we call this acceleration, is effected by a force. So this identifies there is a force present, but the force doesn't act just like this. It's reduced by a factor of the body's reciprocal mass, the inertial mass. The bigger the body's inertial mass, the less the same force will accelerate the body, right? So this looks nice, and the question is, what do these axioms say? We can read both axioms as statements about what a particle does under various circumstances. If no force acts, then the axiom tells us the particle moves uniformly along a straight line. However, if you read the first axiom like a postulate of what a particle does, it is merely a special case of the second axiom. Because if in the second axiom I say the force is zero, the force vanishes, then deviation of a body is affected by a vanishing force reduced by, so there is no deviation from the straight uniform motion. So if you read the first axioms like an axiom that says what the particle does, it becomes a special case. Newton wasn't that naive. He didn't need to emphasize this special case in an extra axiom. And the first axiom needs to be read, therefore, a different way in order to have an important role. The role is the following. You assume that for some reason, we'll come to that, you know that no force acts, and then you use such particles to experimentally check what a straight line is. Okay? So imagine you're in outer space, there's absolutely no force at all, you throw a stone and it does something, and the first axiom instructs you to say, that's a straight line. You are testing the geometry of space. That's the idea. It's a measurement prescription for geometry. So that's this. And then the second axiom tells you if then you have other particles on which a force acts, for instance, because they have charges and they react to some fields, that's a modern Faraday point of view, then the second axiom kicks in. So let me first remark, first axiom, in order to be relevant must be read as a measurement prescription for the geometry of space. And actually we'll add something behind space later. That's the first remark. And that makes a lot of sense, because if in science you talk about an entity like geometry, a straight line, then you better define what it is. Now you might say that's obvious. Well, it's obvious on paper in mathematics what a straight line is, but is it obvious what in nature a straight line is? Well, Newton recognizes this and makes of it a measurement prescription for straight lines. However, there is a second important fact that one observes in nature, and that is that gravity affects all masses, all massive particles. So if I have a massive particle and there is nothing else in the universe, well, maybe if I consider that the self-interaction of the particle with itself gravitationally doesn't matter, maybe the first axiom can be realized. But as soon as I have a second particle in the universe, and I think of gravity as a force, which is the standard view, then I can no longer use this particle in order to measure the geometry of space. Why? Well, there is another particle somewhere, another mass, and in Newtonian theory all particles have mass, and all masses gravitate at arbitrary large distance. So if you have a universe with already two particles, the first axiom can no longer be applied, because its assumption that no force acts can no longer be applied. You say, come on, we never use this anyway, we mostly work with this and it works fine. The axiom is there. It's very important to say what straight line is. If you don't know what a straight line is, you don't know what the deviation from a straight line is. Of course, because we're already educated, we know, straight line, that's a covariant derivative here, or rather the gamma symbols are being determined by this. Deviation, that must be the covariant derivative of a curve. Maybe the covariant derivative of the tangent vector to the curve in the direction of the tangent vector to the curve. You remember a straight line was nabla VV down V on V equals 0. Well, acceleration, deviation from that is nabla down VV is not equal to 0. That's a vector again, because V was, and the covariant derivative makes of this a V. Okay, so you see, if you don't know what a straight line is, you don't know the gamma symbols, you can't calculate the acceleration. You need to know the straight lines first, because before you can even start talking about this. We'll do this more precisely, okay? But that's an important insight. But the point is, if gravity is also modeled as a force, and it acts on every mass, you have a problem. So, since gravity universally acts on every particle in a universe, and of course when Newton says body we think particle, in a universe with at least two particles, gravity must not be considered a force if the first axiom, if Newton 1 is supposed to remain applicable. So we got a serious problem because we don't know how to encode gravity other than as a force. The first one to think about this was Laplace. And it's the Laplace you know. Laplace's question, and Laplace was, what was it, 1749 to 1827. Laplace asked the following question. Can gravity be encoded? Question. Can gravity be encoded in a curvature of space such that its effect, show if particles under the influence of no other force, so we are still in this situation where we think gravity is a force but we want to get rid of it, if particles under the influence of no other force are required, are postulated to move along straight lines in this curved space. That's the question. And in some museums, in some science museums, you see this. There is some throat like this, and you put a coin here, and then you flip the coin, then the coin runs in here like this. Have you seen that? Right, so a bowl shaped like this. Now, of course, it spirals in because of friction. If we imagine, so this is a curved two-dimensional surface, if we imagine we had no friction, you have the idea it goes around like this, and if you give it less energy, it goes on such an orbit and so on. And there is an intuition, could this be the motion of the planets around the sun one dimension higher? That's the rough idea. And well, the answer to Laplace's question, and Laplace spent quite some while thinking about this, but we don't think about it, we use mathematics and it's a two-liner. The answer to Laplace's question is a resounding no. No, you cannot. It's absolutely impossible to come up with a curved space such that this works. Why do we do it then? Well, because it's instructive to see what doesn't work, because we can repair it. Proof. So what is the standard view? So the gravity is a force view. Gravity is a force point of view. And I mean, after all, gravity as a force point of view works pretty well. It just has this slight conceptual difficulty, which is tremendous if you think about it. So let's start with this. That means you have mass times what you call acceleration. This is not the acceleration, but let's not talk about it right now, that comes later. Mass times acceleration equals the gravitational force field. And the gravitational force field, so this is at the point, so it's the naive formulation. You have this, and if it's the gravitational force field, you know that it satisfies Poisson's equation. Poisson's equation is 4 pi Newton constant g times rho, and this is the mass density of matter in the universe. You solve this equation, usually write the F as the minus the gradient of the gravitational potential, then you have Poisson's equation, and Poisson's equation is the gravitational field equation in Newtonian gravity, because depending on the masses around, it determines the gravitational force law. You need to solve this. Once you have it, you can plug it in here to study how a particle on which this force acts, it acts on all the particles, reacts. Okay? Now the thing is, well actually if I write it like this, I need to have a little f here, and there's a little f here and an m here, because the gravitational force is this F. The gravitational force is proportional to the mass of the body on which it acts. That's very special. It's also proportional of the mass of the body that produces it, more generally written here, but it's also proportional to the mass of the body on which it acts, which results in which fact? Which results in the fact that you can cancel out this mass of the body on which it acts altogether, and there is no more mention of the mass of the body on which it acts. Is this true? Well, theory doesn't tell us. Let's go to experiment. Yes. This is called, in theory, the weak equivalence principle, but we can give it names all day long. Experiment decides. So we have here two things. We have a little feather and we have a little bead. Both are red. Okay? Now they're just for fun, they're in this tube. Let me start maybe here. Okay? Now you know what happens. I now erect the tube into the vertical position, and every day experience tells you the little bead will go down like chum, because it has a much bigger mass than the feather. We would say, the people on the street would say, you're probably already more educated in physics, and the feather will just fall more slowly, will be less accelerated, maybe because you think it has less mass. Well, that's okay, once again. So I mean the bead you don't see, you only hear when it arrives down here, and then you look at the feather. The bead falls much faster because they both started from zero speed up here. It must have been accelerated more strongly. That's what you think. But of course, this can all be attributed to the air resistance within the tube. And we'll demonstrate this now. So removing the air resistance by evacuating the tube. So the tube has now been, thank you, the tube has now been evacuated. Okay. Now we do the same experiment again. Air resistance has been switched off. It's not true that the bead is more strongly accelerated than the feather. They're both accelerated the same. Okay, within the error of measurement here. Thank you very much. Okay, well, next proof. So we didn't just exchange the tubes and the bead and so on. It's the same, okay? Right? Ta-da. Okay.
Yes.
Yes.
I have two questions.
Yes.
One is a concept that we have a problem. There are two ways out of the problem. One is we want to keep up Newton's first axiom, but the other one is we could just dispose of it.
Yes.
So why do we choose?
You could dispose of it, and then my next question would be, what do you mean by deviation from a straight line? And then you could refer to the straight lines of Euclidean geometry, and then I asked you, why does the world feature, physical space feature a Euclidean geometry? And I think at that point you say, okay, let's reinstate it and let's see whether we can save it that way. It's a fully conservative approach. Nothing I say goes against anything that's written in Newton's Principia. It goes a little bit about what people made out of it afterwards by using vectors. Yes.
And the
Yes.
second question, so this is the example we usually bring when we talk about conservation of angular momentum. So
This here, okay. Mm-hmm.
right, so angular momentum from the Lagrangian point of view is just a momentum. And in that sense,
Yes.
I could say if there is no force acting, then I don't have a... But what I don't see is if I sit on the particle, why could I not say, so this
Yes.
Körperfest and
No.
Raumfest, why can't I say that?
No. Okay. If you go around in a curved space like this, nobody said that if you attach an additional frame and you return, that the frame still points in the same direction. So this is just the free-falling motion here. But you're probably thinking like you can feel that you go around here and you're like the centrifugal force or something like this. We'll come to this. Okay. So anyway, we experimentally verified, and then we give it the grand name weak equivalence principle, which is, that is great for philosophers without experiments. You cancel this guy. And then you can make an approach towards an answer to Laplace's question. You say, aha, Laplace wants to interpret this, which we interpret as acceleration and force. He says, well, the equation is correct because, I mean, this is numerically checked to very great precision if you neglect relativistic effects. So let's assume the real world is Newtonian. That's the name of the game at this level. And Laplace doesn't say change the equation, put an extra term. Laplace says, let's interpret this equation as an autoparallel equation, because that is the equation for a straight line. So take the f to the other side, and Laplace's question now takes the form, Laplace asks, is this of the form x double dot a alpha of t, so alpha runs from 1 to 3, right? Three-dimensional Newtonian space. Is this of the form x double dot alpha plus gamma alpha beta gamma at the points where you pass x beta dot x gamma dot of t equals 0? That's his question. Is Newton's equation, if there's the gravitational force, can this be interpreted as an autoparallel equation? No, it can't. Why? Because this gamma can only depend on the x where you are, but what about these two velocity factors here? This could only be interpreted as this for, well, not for zero velocity, well, actually not really for any velocity, because if you have any velocity, you can have double the velocity, that's possible, and you would, whatever choice you make for the gammas in terms of the f's, you can't make this match, because you can't get rid of the effect of the x dots in this gamma, because the gamma only depends on x. Well, even if it depended on x dot, it would be very difficult to get rid of these vectors here. So the point is, this simply doesn't have the form of the autoparallel equation. That means one cannot choose, so conclusion, one cannot find gammas such that Newton's equation for this case of the gravitational force takes the form of an autoparallel. But being able to find such gammas would mean being able to find a notion of straight line that could absorb the effect we usually attribute to a force. Okay? It's done. Laplace also found this, not using the autoparallel equation because he didn't have it. He spent several days thinking and he realized there are other inconsistencies which at the end of the day are this one. It is not possible. This standard example from science museums is entirely wrong. Entirely wrong. You cannot curve space that way. Now, what can we do? So we already learned something from our knowledge of the autoparallel equation, from our understanding that it describes straight lines.
You have proven that gamma can be made in any point, but only in this point equal to 0.
Yes. That's another problem.
Yeah, but I would say then one can do it at least in this point.
Well, look, if I let this fall, and then say here it has a certain acceleration, I can make the acceleration vanish there by going to the coordinate system that falls with it. That's that. And now you say, I can fall with it all the time. Can't I make this all along the curve 0? So, well, I have to walk, climb up here and then jump down and let myself fall, let this fall, and then I will fall together with the chalk, okay? The problem is, the Earth is round, and if somebody at the North Pole makes this experiment and thinks of a coordinate system that's falling with him, he will be able to transform away the gravitational force apparently there where he is. But in this falling coordinate system, what if at the same time somebody makes the same experiment down here, in the system of the falling guy up here, this one will not be transformed away, this effect. So a homogeneous gravitational field, like we like it in standard examples, can be transformed away entirely. Come back to that later. But an inhomogeneous one can't. So, but that has to do with your question here, how this can be transformed away. Okay, so this is rather sobering, but in fact, as so often, Laplace didn't look carefully. So the full wisdom of Newton 1 takes us all the way to implement Laplace's idea in a way that works. And what Laplace asked, can we find a curvature of space such that particles move along straight lines? He didn't read Newton 1 properly. Newton 1 talks about a straight line, but it talks about uniform motion along a straight line, not just motion along a straight line. Okay? So the full wisdom of Newton 1 is use also the information from Newton's first law that particles under the influence of no force move uniformly. So if I draw this in a two-dimensional flat space, say, this is uniform motion. These are equal amounts of time, one would say. That's a straight line, straight uniform line. This is also a straight line, but the motion described by this is not uniform because it gets slower and slower. Laplace, in his idea, only implemented this, only tried to implement this. And as it's often said in research proposals, it's a beginning. Okay, but if you But if you don't take things really seriously, you see, starting somehow, if we can't make this work, we won't make anything work. No, you have to take everything into account, and then we start talking. The question is, rather than drawing these pictures, and something that's very difficult to explain to students at first is that a curve is more than the set of its points. A curve is the set of its points and its parametrization, which makes exactly the difference, right? Well, let's make it easier for students. Let's introduce the appropriate data structure to capture this. Introduce the appropriate setting to talk about the difference between these two. Difference easily. And that is something you also know from school. You draw a space-time diagram. If you have a harmonic oscillator, you did this. How does the position depend on time? Well, let's do this for a one-dimensional world. Say this is the one-dimensional world here. And now I have a straight uniform motion that looks in a one-dimensional world like this, agree? And I have a straight non-uniform motion. Well, you can, in a one-dimensional world, the motion is always straight, but the point is here the difference between straight and uniform. Now, rather than showing this and remembering the parametrization, we attach a time axis, and we do not introduce new data, but we just represent the data in different fashion. If these were equal intervals of time, then it's clear how to translate these pictures. This one looks like so, 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 and so on, because every time I arrived at this interval, it's like this. Agree? That's uniform straight motion in one dimension. Well, this is also straight motion in one dimension, but you could easily imagine an extra dimension. It still runs along the x-axis, would be straight motion. But again, equal time intervals would lead you to have, hang on a second, equal time intervals. Now we need to, hang on, I'm confused. No, this is less time, that's the point. This is less time. I'm confused. No, it's the same time for less distance. It looks like this. Exactly, it goes up. I'm sorry, this is not getting slower. I said here it's getting slower, it's getting faster, of course. No, it isn't. I'm confused. Are you also confused? No.
Actually, usually it's acceleration, x and t is exchanged.
Of course. So, yeah. So this is real. So this is getting slower, and this is also getting slower because in equal times it makes less. Yeah. So as a relativist, this is a rather embarrassing moment. Okay. So we're trying to cut it off the video. Okay. Because I don't even have the excuse that in relativity you order the axis differently. Well, I have an excuse because there are no axes, but that's okay. Anyway, so you see the point. The insight is in space-time, if you attach time to space and consider it an entity, this guy here is simply, you can ignore the parametrization because nobody cares whether you now parameterize this curve in space-time in the most crazy manner. Because for every point where you are, you just look at this axis and you know what time it is. You no longer rely on the parameter that parameterizes the space-time curve because you stored the information in the extra coordinate. You freed yourself from parameterizing the curve in a certain way because you stored the information, but even better, in space-time, uniform and straight motion, where the uniform and straight must be said because we always think about time, but in space-time you don't need to say uniform and straight motion in space-time, this uniform and straight motion in space is simply straight motion. No further questions asked. So this gives us a hint. Laplace's idea might work if you only look at straight lines, if you only want to implement straight lines, but it will work in space-time, in Newtonian space-time. This has nothing to do with relativity. It's just drawing what you already drew in school for the harmonic oscillator. It's not relativity. It's just representing the data you have in a different fashion. This goes one-to-one. Okay? But then we can use our ideas about straight motion. Otherwise, we would have to invent new differential geometry that implements straight and uniform motion. It can be done too, but not in that way. Okay, so let's try this. So let's try in space-time. Well, the first thing we need to convert the data into the right form. So let x from R to R3 be a particle's trajectory in space. So this is the usual picture. And now I claim you can convert this back and forth into a world line. That's just a name, a world line. You could also call the world line the history of the particle. Because obviously, if you look at the world line of some particle, you know its entire story. So you can tell jokes in space-time, which today are somewhat outdated. For instance, in Newtonian space-time, this is the joke, Pope, Pope. What is the joke? Two popes meet. Okay, so this is nowadays possible, but this is a joke in space. This is a story. You're telling a story in space-time. Okay, so the world line, somehow this joke never works. I don't know why. Anyway, so you convert from this, you convert this information into that information very easily. You assign to each t now a quadruple of real numbers, a fourtuple, where you just reproduce what you already put in, not a problem, and then you use the trajectory you had before, which of course decomposes in three real functions. That is the world line of a particle. And that is, of course, the picture I drew over there. If you want a more elaborate picture, you can put here the sun, at least a very massive body, and you may put here a very small body, I don't know, me, and we know it does something like this if its energy is not too big, otherwise it will fly away in parabolic or hyperbolic motion as a bound orbit. That's what we observe, something like this. In Newtonian gravity it would be like that. And so this is the curve x, but you know there is Kepler's law of equal areas in equal times and blah, 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 blah. So the parameterization here plays a role. But now you may represent this in space-time, x1, x2, space-time. And what is circular motion or elliptical motion down here in space-time becomes, of course, something, I don't know whether the picture is so good, but it becomes a spiral, right? It's a spiral, and you can look at every point where you are, okay? But obviously, if you're here, you can go back because you just project. You just forget the first component, and you get this curve back. There's nothing happening. No new physics, no nothing. It's just a different way to represent the history of a particle. That's it. That's all it takes to make Laplace's idea work, but in space-time. Why? Well, first, there is a trivial implication from our definition. So the point is, let's assume that on this side, let's assume that x, the little x, we start on the left-hand side, satisfies, again, Newton's law concerning the gravitational force, such that I could already cancel the m. Let's assume this. So now we have a number of trivial, really trivial rewritings. The first one has nothing to do with this. The first one is that I take the 0th component, and this is just a manner of numbering the components here, that I say this is the 0th component of this coordinate map. And you see we are here all in charts. I have only talked about charts. And then you have, and this is not a vector, but this is, this capital X is just a world line coordinates. I just label them like this. And it's very clear that if you take the time derivative of the x0, it's 1. Because it's simply x0 of t is t. You take the derivative, it's 1. Oh, that's very simple. And then from this it follows immediately that if you take the second time derivative, it is 0. Of course, the derivative of 1 is 0. So we keep this in mind, and now we write down a number of equations. The first one is this one. This is simply true, right? This is simply true. Now I write down what is the time derivative of the alpha components. Alpha runs from 1 to 3. What's the time derivative of the alpha components? All depends on t. Well, you need to look, there it says, because the x alphas are the small x alphas, you can use this. And if you use this, we can of course take it to the other side, agree? Minus f alpha of, well, this only depends on the small x's, but you can also write in there the capital X's. Strictly speaking, it's a different function because the function that ignores its first entry. Well, that's not very deep. Let's name it like this. Equals 0. That's it. That solves the problem. You say, hang on, how on earth is this going to solve the problem? Because as far as one can see, you still have the same problem here, and you just added an equation. How can that help? Well, that equation doesn't help. It just doesn't cause trouble. We'll see in a second. But there is something that helps, namely this. X dot 0 is 1. So I can easily multiply here with x dot 0, x0 dot, x0 dot, right? Times 1 times 1. I did not change a thing. How is that supposed to help? Well, these two here, these two equations are perfectly equivalent to the following set of equations. X up a, where a now runs from 0, 1, 2, 3. And here the alpha runs only 1, 2, 3. xa double dot plus gamma a, b, c, x dot b, x dot c equals 0. What is this? This is an autoparallel equation in space-time, right? It's an autoparallel equation in Newtonian space-time. And now you compare the two and you say, oh, yes, choosing in this chart, I mean, we're always in a chart with coordinates, so we can choose gammas. Choosing gamma, we read it off. What are the gamma? 0. If a is 0, what are all the gammas that have a 0 up? Well, they must all be 0 because I have plus 0 here. So gamma 0 up, whatever is down at any point in this space must be 0. I read this off. Now let's look at this one. How do I have to set the gammas that have an alpha up? Well, the gammas that have an alpha up, if they have anything down that's different from 0, alpha up, say 1, 1, then it would produce a term x1 dot, x1 dot, and that's not good. All of those alpha up and beta gamma down, or it even suffices, is 0, but it even suffices if one of the two down is 0, but that could also be the other one. They all must be 0. Why? Because otherwise, if we choose them different from 0, terms come up in this, on this side that do not have this form. So all the gammas are 0, only gamma up alpha, down 0, that must be chosen as minus f alpha at each point. Ah, nice. Alpha, alpha. These indices are set. Now it makes sense with the indices. So the claim is in the chart we started with, which is the chart which in standard Newtonian mechanics is called the obvious chart or the Cartesian chart or whatever. It doesn't matter. We play the game for a time being until we made our point, and then we'll make it more clear. In that chart, you can choose gammas to be given by minus the gravitational force divided by the mass it acts on, so this little f, and the others you choose all 0. Now you say, hang on, and that's the question Kurt asked. Could I transform this away? Because this is just in one chart, right? I could use the gamma transformation law, and we know even though the gamma can be non-zero in some charts, there may be a chart where it's 0. Or there may not be. It depends on whether the curvature vanishes or not. You remember? The question is this a coordinate artifact? Question, is this a coordinate choice artifact? The answer is no, since we can calculate the Riemann curvature, and the Riemann curvature of the connection defined this way, we can calculate it in that chart, R alpha, and the only non-vanishing components, you can calculate the others, and they will all vanish. The only non-vanishing components are those, minus del beta f alpha in this chart. And probably we would rather write it like this. These are the only non-vanishing components. This is actually known as the tidal force tensor. If you study how tidal forces act, you look at this guy. It's the tidal force tensor. It's the Hessian of the gravitational, it's minus the Hessian of the gravitational potential. It doesn't matter, that's the guy. And you can calculate the 0, component of the Ricci tensor. You remember the Ricci tensor? Ricci tensor is the contraction, so that's the components that are left, is the contraction here. You contract the first and the third index, was on the last tutorial sheet. Anyway, it's sub-information, it's traced information in here, and the Ricci tensor is minus del, well, d by dx, so here it doesn't matter to write it so precisely because we're here in these coordinates, it's this. But now you say, oh my God, we know something about this guy because we remember that we had Poisson's law, right? Poisson told us that minus del alpha f alpha is 4 pi times Newton constant times the mass density of the masses that generate the gravitational force. So this is equal to 4 pi Newton constant rho. Ah, interesting. Well, interesting if you know general relativity, because you could call this the 0, component of an energy momentum tensor, and then you got something like R00 equals T00. Okay, so writing, and that is now really, in a sense, cheating, an energy momentum tensor, writing it like 1/2 rho or something like this. You get R00 equals 8 pi g T00. And this is the first of 10 gravitational equations that Einstein postulated in 1912. Einstein in 1912 said in relativistic physics, where a few more ideas come in, but in relativistic physics, he said, you have RAB equals 8 pi g TAB. The point is, this isn't entirely correct, but it's almost correct. Space-time Ricci curvature, he said in 1912, is the energy momentum of matter. We'll come to this. The point is, this is not far from what Poisson's law says. Poisson's law says that for the curvature of space-time in Newton gravity, R00 is 8 pi g T00. Well, that's cheating because I set it to rho, but in relativity, if you have dust, that's lots of particles that don't interact and only have mass, it looks exactly like this. So Poisson's equation, which you all know, makes you understand the basic idea of Einstein's equations, at least the old form, the not correct form. There's an extra term missing here that makes it correct. But that's another issue, and that has to do with relativity and space-time physics, in relativistic space-time physics. But Poisson's law, the field equation for gravity, is right here, and because it's non-zero in the absence of masses, in the presence of masses, the curvature is not zero. If the curvature is not zero, remember the theorem, there is no coordinate system where the gammas all vanish. You have the Earth, you make a non-homogeneous gravitational field, and there is no system where you make, for every particle that you can think of, make the gammas vanish. So it's not a coordinate artifact. It's not like, oh, choose better coordinates and the effect is there. No, it's not a coordinate effect. And wouldn't it be funny if it was a coordinate artifact? Because coordinates are in our mind, but you feel whether you accelerate it or not. Okay? So it all fits together. Okay, so we have this. And so the conclusion is Laplace's idea, Laplace's idea works on space-time, Newtonian space-time. Oh, by the way, you see the gammas that were non-zero, so yet another remark. The gammas that were non-zero were gammas that had time indices. Well, here we think of them as time indices, has to do something with this extra direction, right? This shows it's not a curvature of space. For instance, the Riemann tensor in components alpha, beta, gamma, delta, they're all zero, where alpha, beta, gamma, delta run from 1 to 3. It's not a curvature of space. The space-time is not curved in the space directions, roughly speaking, in this Newtonian space-time. It's curved in the extra direction, together with the space. You understand what I mean? Okay. So here you see it's really space-time curvature, not space curvature, but space-time curvature that works. The only one that's not vanishing is this one. But that means not all components of the Riemann tensor vanish. Yes?
I have a question on the autoparameter equation. The right side is 0. This certainly transforms as a tensor. On the left side there is x double point and gamma x point.
Yes.
X point. Gamma does not transform.
As a tensor, but the x double dot neither. Thank you for the question. So, very good question.
Neither the velocity nor the acceleration transforms.
The velocity does, the acceleration doesn't. Well, let me write it down. Okay, so question, what about the transformation behavior, Trafo behavior of left-hand side of x double dot alpha, no, A, plus gamma ABC x dot B x dot C equals 0. Well, this guy here, you may remember, is this guy. We calculated this. So if you take the derivative of the velocity in the direction of the velocity of a curve, the 8th component is this here. This is the 8th component. And this is again a vector field along the curve. And this guy is a vector field which we call the acceleration A. A. Yes, yeah, it is A. Let me make a fancier A because I also have an index A. This is the acceleration vector. I told you the acceleration is a vector. The acceleration is a vector. But the second derivative of the components of a curve are not the components of that acceleration. This belongs to it too, and only the sum of the two transform right. And you know, these transform as vectors because they're velocity components, we checked that. These do not, and in the same way, no, in the opposite way in which the gammas do not transform as tensors, as a 1-2 tensor, in the opposite way, this doesn't transform as a vector, as vector components, but the sum of the two cancels the troublesome terms, and only the combination deserves to be called the acceleration. You can't say that's the acceleration and that's an extra acceleration. No, this together is the acceleration. And of course it's chart independent. If you sit on a rocket, you feel whether you accelerated or not. How crazy would it be if somebody thinks another coordinate system and you feel something different? It won't happen. Okay? This together is the acceleration. Okay. Now, we have thus reformulated Newtonian theory such that gravity is a curvature of Newtonian space-time, and the first axiom now takes the form: particles under the influence of no force, but gravity no longer counts among them, under the influence of no other force, moves along, has a world line that is straight, but a world line is in space-time. End of message. This is Newton's first axiom. You don't say uniformly straight in space, you say straight in space-time, the world line. And if you now have gravity and you throw two particles, say that's the Earth, right? Small Earth. If these two particles, you drop them and they will start doing this, right? There will be convergence of these lines. That's another way you can identify curvature, that geodesics that are originally parallel start converging. Think of the surface of a sphere. You go from the equator up parallel, equator, you go up parallel, but finally they meet. Okay? That's another effect that you have when there's curvature. It's called geodesic deviation. So we solved our problem. We just have to accept that space-time is curved, but your space is still nice and flat. But space-time is curved, and the first axiom can be put into practice. Case closed, up to the point that, of course, we have a terrible coordinate-dependent formulation here. All was with components. What is the real structure behind that? So that's section 3, adequate, a sketch, or the foundations, because I have no time to do this all, the foundations of the geometric formulation of Newton's axioms. And again, this is not new physics. This is just what Newton wrote down in words, implemented properly with the mathematics that makes it work rather than that the mathematics that seems to make it work. Okay, so the key definition, I just sketch it and I tell you where it goes, but maybe you're able to fill in the following steps yourself. Definition. A Newtonian spacetime so this is now, we have a new start, okay? So this is just in our mind, this changed our philosophy a little, and now we start talking seriously, okay? So a Newtonian spacetime is a quintuple of structures, and about every single structure here, Newton talks, okay? It's a set with a topology, continuous curves and so on, it's smooth, we can talk about derivatives. We have a covariant derivative, of course we do, because Newton talks about straight lines, uniform straight lines. We translate this into straight lines in space-time. And Newton also talks insistently on something called absolute time. We have an absolute time t, where MOA is a four-dimensional smooth manifold. A four-dimensional smooth manifold that has no direction. This is space and this is time. There's a danger in the word space-time. The danger in the word space-time is that you misspell it. You could misspell it like this, space plus time. This is not space-time. Space-time is one thing in which, at first, you cannot distinguish between space and time. It's just four-dimensional, like the sphere. The sphere is two-dimensional, but you wouldn't say where's one direction over the other. Well, okay? Space-time, and only you start with this, and then you may have a derived notion under certain circumstances what is space and what is time. Okay? So space-time is a four-dimensional manifold. Don't think you already know what it is. Delete all your memory. It's a four-dimensional space-time with a covariant derivative and this. This is this. And t, this is clear what this is, a covariant derivative. And t is a smooth function on the manifold. So absolute time is a smooth function. T from M to R is a smooth function. And Newton says things. He says two things which we convert into axioms, into requirements, I should say satisfying, which we convert into axioms for these two structures. One thing Newton says is that there is absolute space. That's what Newton says. There is an absolute space. This will take the following form. You say, oh, we didn't provide for absolute space. We only provided for an absolute time, whatever it is. But it can be derived. There is absolute space is this. It's the requirement that the gradient of the absolute time function doesn't vanish anywhere. It's non-zero all on the manifold. So if you take it at a point P, at every point of the manifold you require that this absolute time function has non-vanishing gradient. What does that have to do with there's absolute space? So this is no longer part of the axiom, but that's something that follows from it. You define absolute space S tau, it's absolute space at time tau. Absolute space at time tau is the set of all the points of the four-dimensional manifold that satisfy the condition that t of the point, well, if t is a smooth function on the manifold, then every point can be assigned a t of p. Every point of the manifold, every event in space-time is given a time, a universal clock time, okay? And the space, the absolute space, tau at time tau, is the collection of all the points that have the time label tau, as this says. And then it follows by this dt non-zero, it follows that the entire manifold is a disjoint union. And the disjoint comes from this, is a disjoint union of all these spaces. Or in other words, if you like pictures, if I do a three-dimensional space-time, because I can't draw a four-dimensional one, space-time foliates. Foliates in all of these S1, S3 half, S pi, and so on, right? It foliates in all these spaces, and the universal clock gives the same time for all these points here. As long as this is a smooth function and the gradient vanishes, if the gradient would vanish, you would have, so you look at it from the side, so this would be S1 and this would be S a little later, if it would vanish for quite a while, S2, they would intersect here, right? That would be a point where if these are level lines of the global time function, of the absolute time functions, at this point P, there would be a problem. Therefore, we exclude that. Okay? So, so this innocent requirement on the absolute time yields you a notion of absolute space, and of course that's how we think of space-time. There are spaces stacked together to give space-time. You say, but they're stacked together in a strange way. I mean, why are they like wobbly? Well, what do you mean by wobbly? Have we talked about shape yet? No, we haven't. Okay, good. Then Newton goes on and he says things like time flows uniformly. So absolute time, he says, absolute time flows uniformly, Newton says. What does that mean? With 1 second per second? Right? I mean, what is that supposed to mean? Where, if you want to be clear about it, you say that the covariant derivative of the gradient vanishes everywhere. So if you put here an x, for any x, this is again the zero covector field. You say this is zero at all points of the manifold. So everywhere. It's already written as a field equation. This means absolute time flows uniformly. How do we understand that this means absolute time flows uniformly? Let's see in a second, okay?
I have a question.
Yes.
This with respect to any vector field on the smooth uniform?
Yes, that's if this is open here, so you could put d by dxa here in any coordinate system on the manifold, and then you take the bth component, and then because this is C infinity linear, and certainly C infinity linear, if I put something here, this would be a 0-2 tensor field. So if I leave this slot unfilled, then this is a 0-2 tensor field. And I can require that to be the 0 tensor field of that type. If you don't like it in this form, we'll do it in coordinate form a little later, but I maintain that this equation is good, and this is an equal sign on the space of 0-2 tensor fields. Anyway, so let's do this in coordinates in a second. Yes?
That problematic point, would it correspond to saying that time stopped there?
Yes, time would stop for a while, right? Because, yeah, that's what the gradient is, no? If you draw the level surfaces, if the gradient gets, yeah, you know, if this goes together, yeah, that's right. Time would stop here. That's correct. And that's, of course, meaningless. It's not what we want in physics, but it could be if we just say it's a smooth function. So we have these two axioms. You see, this is a compatibility axiom, because it relates these two things Newton talks about so eloquently, but that's sometimes a matter of a heated debate what exactly this means. Well, this is, well, a proposal. This is a clear formulation of what it means, and this you can make work. Okay, so well, if you bear with me for 10 more minutes, I can sketch a little bit how it goes from here on, but I won't do the full thing because actually my main point for the purpose of these lectures was made before, that you can view gravity as a curvature of space-time already in Newtonian mechanics, okay, and that this viewing gravity as a curvature of space-time, even within Newtonian mechanics, is not just an alternative formulation, which of course is the more agreeable point of view to take, but really if you look at the first axiom and say, what other choice do I have? Okay. Anyway, that will be exactly the philosophical point of view, the approach in general relativity later, and I wanted to show to you that already in Newtonian gravity, that gravity effects can be understood as a curvature of space-time has all to do with gravity and very little, or rather nothing, to do with relativity. It's not relativity that forces us to space-time as far as gravity is concerned, it's gravity itself. And the understanding of the relation between geometry and gravity and all of that. Okay, so I think that's the most important lesson in there for a theory builder. But anyway, so now we have this nice definition, and well, now we can make definition, a vector x in some TPM in space-time is called a future-directed if the application of the absolute time function to it yields a number greater than 0. The vector is called spatial. It's a spatial vector in the sense of absolute space if the application of the gradient of the absolute time function is 0. And it's called past-directed if, you guess it, dt of x is less than 0. What does that mean? Picture. You have the level surfaces of your absolute time function, which are called the absolute space at the various times. And you now take a point in one such absolute space, which however is also a point in space-time. And you have a space-time vector, say this one. Well, now it depends on whether this is S2 and this is S1, because then time increased from here to here. And then this one applied the gradient of the absolute time function, which is a covector, covector field applied to this vector at this point, yields a positive number. So this guy is future-directed, whereas a vector that points what we intuitively would call tangent to the surface, this guy, this is spatial. Well, of course, it's a tangent vector to the level surface of this. Of course, the gradient on the tangent vector of a level surface vanishes. It's this old theorem. And if you had a vector pointing here, this would be a past pointing or a past directed vector, right? Okay, so the impact of this is definition, or rather postulate, or rather Newton's first law. Newton 1, it's still Newton 1, it says nothing different. It says the world line of a particle under the influence of no force, and I remind you again, gravity isn't one anyway, in this view, isn't one anyway, is a future-directed autoparallel with respect to the nabla we have on space-time. And a future-directed curve is a curve that has as its tangent vectors at every point a future-directed velocity. Okay, so a future-directed autoparallel means that's an autoparallel. So you have nabla v world line x on world line x is 0. That's autoparallel, no force. Acceleration is 0. And you have that dt of the velocity is greater than 0 everywhere. Of course, the particle runs into the future and not into the past. In space-time, you need to make the distinction between future and past, right? Okay. That is this. That's Newton's first law. No more funny talk. Now, there is an interesting question about what this formulation can give you other than a nice formulation of Newton 2, which I also write down in short form. Newton 2 is simply the acceleration of a world line, which is of course this guy. If it was 0, it's unaccelerated, is a gravitational force, is a force, not a gravitational, not gravitational, is a force, so where F is a spatial vector field. Because a force is only supposed to accelerate you in the spatial directions. Okay? So you can prescribe a vector field. It's only a force if it's a spatial vector field. Then you have this. That's Newton's second law, and if you like, it's m times the acceleration is the force. Nobody said that's wrong. I only said the acceleration is not x double dot. Okay? So that's Newton's second law. Now, let me introduce one more piece of one more idea, but that's more or less just a convention. And then we have another, I believe, good insight. Convention. We have this absolute time function, right? It's given to us as part of the structure of the manifold. The convention would be restrict attention, but that's really a convention. You don't need to do this. It's just incredibly practical. Restrict attention to atlases A stratified. We call them a stratified atlas. To atlas A stratified, whose charts UX have the property. And now, of course, if you're a geometer and you say, oh, you know what? You can require on your charts whatever you like as long as they still cover the manifold. I don't care about your charts because your charts are in your head. So this is not it's really a convention. Let's only think of those charts because, okay, that have the property that the zeroth, you know that this chart map comes on a 4-dimensional manifold in terms of 3 coordinate functions, right? And so on, that have the property that the 0th coordinate function coincides with the absolute time function. Why can you do this? Well, the absolute time function is defined on all of M, so you can always take the restriction to a chart domain U, because the other coordinates might not be defined on all of them. But so the x0, which is defined on U, is just the absolute time function that exists everywhere globally by axiom, by Newton's talk. Let's do that. It's just clever because otherwise you have an atlas. You can choose an atlas that disobeys this structure and all the formulae are right. It's just the formulae become simpler if you make this choice. And because you have the data, why not use it? Okay, to make life simple. But it's really to make life simple. Nothing depends on it. Okay, very important. A stratified atlas. And in the stratified atlas, we can now evaluate this guy with some insight. You know what this is. This guy we set is 0. That is the time flows uniformly talk. Absolute time flows uniformly. Nice. What does it mean in a stratified atlas? Well, it means this guy here is of course then just a dx0, you agree? In any direction, so for any d by dx a running from 0 to 3, right, is 0. But this guy is, because there's the dx, it's the minus gamma symbol, you remember from yesterday? This is minus the gamma, or day before yesterday. This is minus the gamma symbol, and it has the index a down here. This 0 comes to lie here, and there is another b here, because the whole thing is a one-form field, so there's the other b. Okay? So you see that all the gammas, whatever is down from 0 to 3, all the gammas with an index 0 up vanish. That is what this thing says in a stratified atlas. In a non-stratified atlas, you get extra terms, but they're all coordinate artifacts, because you could go to a stratified atlas. Okay, you can always do that, because that is always a global function, and then these guys vanish. Now let's use this and let's evaluate what Newton 2 says. So let's evaluate in a chart Ux of a stratified atlas, a strat. So actually everything is said. There's nothing more to be said. What I'm going to do now reconnects you with chart physics, which we're used to, and we'll recognize terms we always interpreted in a, I would say, rather peculiar manner. Newton's second axiom, Newton 2. What is Newton 2? Newton 2 says nabla, velocity of the world line is f by m, right? That's what Newton 2 says. Now let's write this in coordinates. In the chart, this takes the following form. X, I do the 0 component separately, because then I can discuss it better. X0. Now, did I say anything about how the world lines are to be parameterized? No. I said a world line is a future directed curve, right? That satisfies this. So also here, Newton 2 says X is a future directed curve, like in the first axiom, right? And then this is true. I didn't say anything about the parameterization, so you could have chosen any. Let's call it lambda. And then the autoparallel equation says take the x0 component, derive it twice with respect to lambda. Then comes gamma 0, AB, xa prime, xb prime equals 0 with respect to whatever parameter you chose. Do you lose information about time? No, you go to the point, you evaluate the point with the absolute time function, you have the time, whatever your parameter chosen. Now I write the other three all at once with alpha, so alpha is from 1 to 3. So Greek indices always run from 1 to 3 and Latin indices from 0 to 3. X alpha double prime plus. And now I split up what happens here. So I have the alpha. Now like here, the alpha. Now I have AB, XA prime, XB prime. But I like to resolve this Einstein summation convention somewhat. I could have that these two guys are just, okay, now I call them alpha beta, is not clever. Let's call them CD. CD, okay. So I now, for the alpha, gamma alpha, I have, they could be both indices 1, 2, 3, okay. Then I have here, by extension of the summation convention, this. But then I forgot terms, okay. I forgot the terms where I have both of them 0. I have x0 prime, x0 prime, okay? But I still forgot terms. I forgot the terms where I have a beta, a gamma down. One is 1, 2, 3, and one is 0. So I have x gamma prime, x0 prime. And I forgot yet another. I should have said something. I'm sorry. I forgot something in the axioms for Newtonian space. Please add to the axioms. I'm sorry. add two axioms of Newtonian spacetime. Now I made a postulate on the t, namely dt non equals 0. I made a postulate on the compatibility of gamma and t, nabla and t, namely nabla dt is always 0. And the third one, I forgot, is a postulate on the nabla alone. Nabla is torsion free. I'm sorry, I forgot that. Nabla is torsion free. One condition on the absolute time, one condition on the covariant derivative, and one compatibility condition between the two. I'm sorry. So you have this. But if it's torsion free, we still miss a term, namely where the first one is 0 and the second one is gamma. But that is the same term if it's symmetric down here. So I get a factor of 2. And I bet you all spend a lot of time in your lectures on classical mechanics deriving this 2. And the right-hand side is of course not right. Here we have f alpha divided by m. And there it's 0 because that's the f0. In a stratified atlas, f0 is of course 0 because dtf is 0. So this is Newton's second law written out. What on earth do we learn from that? This isn't even time. This is an arbitrary parameter. Well, in a stratified atlas, this guy goes out. So in a stratified atlas, we can immediately conclude x0 double prime of the parameter lambda is 0, meaning x0 of lambda equals a lambda plus b for constants ab. Agree? What is x0? x0 is t is x, little x0 after the world line curve x, right, of lambda, but that is t after x of lambda in a stratified atlas. Meaning the time of a point along a curve runs proportionally to this parameter lambda, or rather the other way around. The time is given, the time function, and the 0th component, which you say, well, that I'm really not interested in, that's just garbage. And you remember before, we had this as the 0th equation, we inherited this, and it was trivially true and so on. So you see, in a stratified atlas, what we did before in the first part, where we had a 0 here, that's only true in a stratified atlas. The point is the space-time diagrams I drew in the first part of this lecture, I already assumed, I cheated because I said that's space and that's time, let's do this. Well, I assumed that space repeats itself like this, right? In a stratified atlas, if this was a chart picture, it wouldn't. But in a stratified picture, it also looks in a chart atlas like this. So what I did was right, but now I understand why. Because I already used the global time function in order to define the spatials. The spaces. Yes?
I got me confused. We started out with constructing our formulation in a way where we set those capital gamma 0 Ct to 0. Because we started with demanding that Newton is valid.
That was the first part of the lecture.
Right.
Yes.
The only difference was that there were dots instead of the primes. So we said, okay, let's demand that gamma has this property of having mostly zeros. Now we say, okay, let's formulate this in a manner which has the mathematic.
That's right.
And now we are happy to recover that the gammas are zeros.
No. It's right. So the first half of the talk, until I started this section, was starting with what we always write down and somehow working your way to an understanding that you say, somehow this looks better. But now we were always caught in a sense of preconceptions, of superstition, or of preconceptions about charts and what it means to have a Newtonian spacetime. This was rather formulated in a vague manner, in a non-geometric manner, always in charts, and we went up. Once we were there, we had some insight. We say we need a proper geometric formulation. Then I made a cut, forget everything from before. I start now with this abstract definition. I reformulated both of Newton's laws in the new language, but now I need to start from I can no longer use what I had before from Newton's laws in charts. I need from this reformulation I had in this section, I need to derive what I had. That's right. And there is no assumption on nabla being flat. It's not a flat connection. I didn't require this anywhere. Okay, I only required this postulate. So it's right, we're coming the other way down, and you can now not look at this derivation with these prejudices. You can't cross-link them, that's dangerous, right? So, okay. So the definite statements are these, that's my point. Okay, so that's the stratified atlas, but now look at this guy down here. What on earth is this? Well, once I saw this, I can see, I could get the idea. No, I could, for convenience, so it's a convention, I could parameterize, it's just convention, parameterize the world line by absolute time. So by the number, by this number here. And then you find that what before was d by d lambda now is a times d by dt, but for a constant a. So you can convert these primes into dots, if the dot is the derivative with a, down here. Let's do this. We do this twice, so instead of double prime, we get double dot with a factor a squared. A prime and yet another prime both become dots with a factor a squared. A prime and another prime both become dots with a factor a squared. A prime and another prime both become dots with a factor a squared. And over here, you don't have an a squared. But you can now divide on both sides by this factor a squared, which is just the unit measure of time you use, right? So the whole left-hand side becomes free of it. And only on the right-hand side, if you write down your force law, you need to decide, for instance, in Newton's constant, on what units of time you have, seconds or years or whatever. So there it survives somehow. It's a choice that is usually absorbed into here. Okay, fine. So we have this equation, so we have that. Now here you have what you would usually call the acceleration, but which isn't the acceleration, because what is the acceleration? All of this. All of this is the one and only acceleration alpha component. No summand in there alone, or any combination of summands that isn't all the summands, is acceleration. Because none of these terms by itself, or if any of these terms is missing, this no longer transforms as a vector. Okay? But acceleration is a vector, because if acceleration as a vector is a tensor, if a tensor has vanishing components in one chart, it has vanishing components in any chart. But chart is now a chart on space-time. For instance, you have a chart like this. Now imagine you twist the chart like this in space-time. What do you get? You get a rotating coordinate system. But in space-time, it's one chart. One chart that's constructed like this is a rotating coordinate system in space. It's one fixed chart in space-time. Isn't that clever? Or now you can do this wiggle, yeah, and that's it's that chart, but it's one fixed chart in space-time, describes the view of a dancer, right? If you want the coordinate system of a dancer who carries the coordinate system with him or something like this. Okay. Anyway, not a single one of these is an acceleration all by itself. Now, what if we have the presence of gravity? Yes?
Question. I see when you introduce this a factor, I see on the left side how a squared emerges, but I don't see on the right side.
It doesn't, and I divide it through.
Yeah, but then 1a emerged there. I don't see how.
There's an a squared.
Ah, okay. Now it's good.
Okay, so I forgot the square, yes.
This symbol you're using for the acceleration is
This is an A. It's a small a. I just used the script a because I had an index a over there. Okay, it's the a for acceleration. Okay, Now, let's discuss this very quickly. In the presence of gravity, these two guys we would set to the gravitational force little f alpha, right? So that would contribute a term to the acceleration due to gravity, and a term that cannot be transformed away. Additionally, there could be also sitting in this guy, in the gamma alpha 0. So let's say there is no gravity. Let's get rid of gravity. If there's gravity, there's a contribution here. Let's assume there is no gravity. And let's indeed assume if there's no gravity, you know, in gravity the only gamma that is non-zero, if you use the right chart, is this one. You can make all the others zero. If there's no gravity, you could formulate this as Newtonian spacetime is flat. In the absence of gravity, Newtonian spacetime is flat, right? And if there's gravity in a certain system, it's this gamma. You can reformulate this also fully geometrically. I spare you this. The point is, in the absence of gravity, you have a coordinate system where all the gammas vanish. And you say, oh, that's what we always said. X double dot equals f alpha by m in a system without gravity and in a very special coordinate system. Now, let's assume this case. You go to this very special coordinate system and you don't have gravity. This looks all normal. But now you get the idea. Let's view the same physics in a chart that's twisted in this direction, which is one chart in space-time, and which we would call intuitively a rotating chart, right? But it could also stretch, could do all crazy stuff. Then, of course, in that chart, even though in the previous chart all the gammas were zero, all kinds of gammas pop up. And assume we use a stratified atlas, this is not affected. Now, what do these terms mean? Well, this term is only spatial indices. It means you chose a chart, for instance, a polar coordinate chart. So without using a twisted chart, you have this Cartesian chart, as you would call it. Now you choose polar coordinates in space, but you leave time untouched. You did this 1,000 times in classical mechanics. These guys appear. These guys appear. They're the correction terms in polar coordinates. This doesn't appear, and this doesn't appear either. Now you go to a rotating chart, and in order to really say what rotation is rather than rotation dilatation, you already need to establish a metric on each spatial section. We haven't done that yet for a good reason, because the idea that each absolute space carries a metric is an inertial system fiction. In a non-inertial system, the geometry of spaces is more complicated than a three-dimensional metric geometry. I'll comment on that maybe in a second again. So anyway, assume we can talk about a rotating system, finish in a second. This term here, x dot 0, in a stratified chart, there will be no more x dots, and this one will go too. This one here will be a term that's independent of velocity, but will depend on what we usually call the rotation, the angular frequency of the rotation of the chart. This will be the centrifugal, what is usually called the centrifugal pseudo-acceleration. This here has a 2 here. It's proportional to the velocity, to the spatial velocity of the particle. It will have the omega in it too. I mean, you can do much more complicated stuff than rotating. The omega in it too. This is with an omega and with an x dot, and the omega may come in various ways. This is the Coriolis pseudo-acceleration. Look at Wikipedia how you get the 2. Okay, I don't understand that argument, but the point is the 2 is because the space-time has no curve, has no torsion. It's because of these two terms appearing twice. Okay, that's the 2 of the Coriolis force, which really is hard to explain usually. You have to do some hand waving. The centrifugal pseudo-acceleration and the centrifugal and the Coriolis pseudo-acceleration. Why do you call them pseudo-accelerations? Well, because you feel something isn't quite right about them as an acceleration. Of course there isn't, because neither this is an acceleration, nor that is an acceleration, nor that what you're absolutely certain of is an acceleration, but only this one plus this one plus this one is an acceleration. Now in a rotating system, this will no longer be 0 if before you had a uniformly free moving particle. This will not be 0 anymore, and this will not be 0 anymore. But the sum of these will remain to be 0 because it's the acceleration of the particle who doesn't care whether you're thinking about a rotating coordinate system or not. Right? The acceleration is totally unimpressed by your fantasy about what coordinate system in space-time you have. That's all. Thank you very much. If there are no questions, we reconvene at 1:15. There is a question, okay.
You were assuming that the torsion is 0 as one of the additional axioms.
Yes.
I mean, I understand that this makes this nicer here.
Yes.
Problem, but we didn't get that out of the first half of the lecture of the Newton's, starting with Newton's axiom.
There we didn't need it because we assumed first all the gammas are 0 and then we're forced to see some are not. The first was coming from prejudices to a certain level of understanding and then saying in order to get rid of all the dead bodies we left on the side of the road, I didn't talk about, pedagogic omission of truth, I then formulated the next section where I come top down and everything I said before, I said to give you an idea how you get there. And what is said in this last section is the definite formulation you should give Newton's words. So I initially thought about starting the lecture with the last section, but that is somewhat abstract if you haven't understood the idea before why you would even be prompted to go there. And you would get the idea, well, if I do everything in a special chart, then everything was fine anyway. This is all unnecessary sophistication for sophistication's sake. The first part was to say, let's start with what we always think is the right way to present it, and let's see where the problems lie. But then we need to have a fresh start. This is the fresh start.
Still, I don't think we need the torsion free because we're talking only about the autoparallels, which are not impressed by torsion anyway.
They are. The autoparallels are impressed by torsion. It's dangerous. If you have a metric compatible connection, which comes in the next lecture, and you add torsion or not, the autoparallels are impressed. Okay? You say they're not impressed because you have a symmetric contribution from both there. That's right. It depends on where you start and what exactly you require in which order. This is a notoriously confusing statement that torsion does it or does it not affect the autoparallel equation. The answer is it depends on how you define the connection starting from given structures. In one way it depends, in the other one it doesn't depend. Although by just staring at the equation you say the antisymmetric part falls out, but the question is, does already the symmetric part have a torsion squared in it by some construction mechanism? We just postulate it, then everything works out like we like it. And the same is true in Newtonian, in Einstein gravity. You require that the connection you use is torsion-free, and you have a compatibility condition not to the time function but to the Lorentzian metric of space-time, which philosophically replaces the time function. It's just that the sections it makes are no longer like this, but they're like the cone. And everything here is time-like, and everything here is space-like, right? And here this was space-like, and this was time-like, and everything this was, and so on. Okay? But the Lorentzian metric is not the generalization of the spatial metric. You can think of it that way, but it's particularly non-insightful to do. It's the generalization of the absolute time function. Thank you very much. Yes. Okay, right.
Suppose I'm in a rocket and I turn on the engine,
Yes.
then force depends on time. So how should I use the Newton's second law in this case? I cannot, or what happens?
Well, I said it's a spatial vector field. That means that dtf is 0. But I said f is a vector field on space-time. So I don't see why it wouldn't change if you proceed in space-time. It's just it doesn't have a component pointing there. So say if I draw a little picture, say these are the equal time surfaces, then I say the force points like this, it doesn't point out, but of course at another point it could be different, so you're just switching off the rocket and now you're switching it on again. Agree?
Yeah.
So that is captured, of course. Any more questions? Yes?
I have an idea that in this formulation you can very easily reach Euler-Lagrange equations.
How you get in this, the Euler-Lagrange equations? Yeah. Yes, you can't before you do not understand how to establish a metric on the spatial sections, because in the Euler-Lagrange equations they invariably take the form like this. Some books say in most systems they take this form. No, in all systems. The point is that G here, the T here is the velocity to the spatial curve, okay, 1/2 m, and you need a metric on space to do this, okay? And when the book thinks it doesn't have the form of the standard T, well, it's just a transformation of the components of this G in other charts, like polar coordinates. So in Newtonian mechanics, always the Lagrangian has this form, and this T has this form without the square root, because on space, Newtonian Lagrangian formalism works over the spatial section only, because if you put the square root, you have reparameterization invariance, you get straight curves, but not straight uniform curves. If you take this away, you fix the parameter automatically, you get straight uniform curves. That's the reason for the kinetic energy being like this without the square root, to get straight uniform curves rather than straight curves. But this is a solid spatial picture. This doesn't work in the space-time, and it cannot work in the space-time, as I said, because only in inertial systems, which by the way are defined as coordinate frames xa d by dxb by coordinates that satisfy this. These are inertial frames. Non-accelerated, non-rotating is this, because only in such frames where you then have the equal time functions can you establish a spatial metric everywhere. If you go to a rotating system, well, physicist's intuition tells you, if you go to a rotating system, what do you need to know? You need to know the omega vector, the frequency, right? Well, it's actually an omega covector because it has to do with rotation in planes, but apart from the G, which is a 2 tensor in space, you need a one form to know what's going on. So in fact the geometry is given by a metric and this omega and stuff like this. So really having a metric of space is an inertial system fiction, and in an inertial system you can make this working and running. And then you can, by calculational truth but zero structural insight, you can change coordinates to depend also on the time t. Okay? The formulae of Lagrangian mechanics stay true, but it's somewhat out of the initial formulation of Lagrangian mechanics to go to rotating frames. And then you pick up all these terms and so on, but you don't really understand them. Okay? So there are lectures in German on the web, on my classical mechanics lectures. It's a second-year undergraduate lecture, where I follow this approach to introduce classical mechanics, and I finally come to Lagrangian mechanics. That's in German, it's on the web. So if you want more on this is kind of some, I don't know, 40 hours lectures. Okay, I'd say we stop here and we reconvene at 1/4 past.